This week, we're going to look at what happens when we actually stress a system at equilibrium and how that system shifts to counteract that stress. This is Le Chatelier's principle. This probably came up when you were working on last week's assignment, and this week we're going to look at it in a lot more detail. So Le Chatelier's principle is that if a system, an equilibrium system, is disturbed by changing the conditions, the position of equilibrium will shift to counteract that change. Remember, equilibrium is all about rates, that forward and that reverse reaction. So if we were to increase the amount of products or decrease the amount of reactants or increase the pressure or decrease the pressure or increase the temperature, we're going to stress the system. Now that's going to cause the system to want to reestablish an equilibrium with those new conditions. And to do that, one of the rates will speed up in order to reach equilibrium and in order for equilibrium to be reestablished. The first way that we're going to look at is concentration changes. So we can change concentration by adding stuff or by removing stuff. That will stress the system at equilibrium. Now, you'll see in this top diagram, we have this original mixture. As we add things, like so Fe3+, the mixture appears more red. Or as we add as we remove things, maybe by adding hydroxide, it starts to appear more yellow. So you can see in this diagram that there are different equilibriums based off those colors, and those are responding to different stresses. Let's look at what this looks like on the graph. So here we want to look at some different changes. Let's first maybe look at what happens when Fe3+ is added. So if I add Fe3+, if I look at the graph, initially it's going to go up. So at this point, it says SCN, let's see Fe3+. I add iron 3+. Initially, this graph is going to go up because the concentration of Fe3+ is going up. Now, what Le Chatelier says is that if the stress is increasing iron, the system wants to counteract that change. So the system wants to use that iron up and bring it down. So the stress is to increase the amount of iron. The system wants to decrease that iron ion. Now, in order to decrease it, the system has two choices. It can either move to the right and produce more of this ion, or it can move to the left and produce more of the other side. So the stress is to increase iron 3+. The system wants to decrease it, so the system is going to shift to the right because that will use up more iron 3+. On our graph, that means that iron 3+ is going to go down and then reach equilibrium again. The thiocyanate ion is also going to go down and then reach equilibrium. And then that iron thiocyanate complex is going to go up and then reach equilibrium. Now, the amount they change is important too. If you remember last week, that's dependent on coefficients. All these coefficients are the same, so they're all going to change the same amount. So then we reestablish this new equilibrium at that point in time. So now we have a new equilibrium due to changing that. Now, what if we were to remove something? So maybe I remove my thiocyanate ion. We'll talk about how to do that in a minute. So if I look on my graph, thiocyanate is going to initially go down. I will see one thing dropping because its concentration is going to change. If we think of the stress is a decrease in thiocyanate. The system will want to counteract that stress, which is an increase in thiocyanate. In order to increase the amount of thiocyanate, the reaction needs to favor the left-hand side, or the reverse reaction. So we are going to have our amount of thiocyanate complex is going to go down and then reach equilibrium. Our thiocyanate ion is going to go up and then reach equilibrium. And our iron 3+ ion is going to increase as well because it's on the same side as the thiocyanate ion. So whenever we're talking about changing concentration, we want to identify the stress. We want to identify how the system will counteract that stress and which way the equilibrium will shift as a result. Now, the one thing to note is how we actually remove things. And that's often the most confusing for students. Because if I were to say that I added sodium hydroxide, a common response for students is that it's going to have no change on this equilibrium system because nothing is there. However, when we're adding things that are not present, our first question needs to be, what could we be removing? I know that iron 3 plus reacts with hydroxide ions to form insoluble iron 3 hydroxide. Now in that way, the iron 3 plus is going to be removed. So this will be removed because it's forming a precipitate and it's no longer a part of that system. Now it's always, in the case of our course, it will be the most simple ion. So if it needs to, it'll be on your solubility chart. Otherwise, it's not really fair of me to ask you that question. However, if we are adding something that isn't in our reaction, we need to first consider what could we be removing. And to do that, we look at our solubility chart. The next way that we can stress a system is by changing the pressure. If you think back to Chem 20, we talked about Boyle's law, which is if we decrease the volume of a container, the pressure goes up. If we increase the volume of a container, the pressure goes down. So there is an inverse relationship between volume and pressure. Now, equilibrium will shift to counteract whatever stress is imposed on the system. So if pressure goes up, the system wants to decrease the pressure. If pressure goes down, the system wants to increase the pressure. The way that looks for these systems of gases is we need to look at the amount of moles of gas. If we look at the Haber process at the bottom here, on the left-hand side, I have 4 moles of gas. On the right-hand side, I have 2 moles. It is important that we only care about the gaseous ones because that's what's going to contribute to the pressure. If we think about this, the side with more moles is going to have a higher pressure. So this side would be the side that would increase pressure, and this right-hand side would be the side that decreases pressure. So when we look at changes in pressure, we need to look at the moles of gas when we look at how to counteract that change. So here we have a system. So the first thing we do is we decrease the volume. So we decrease the volume, which means I increase the pressure. One thing we'll notice in these types of graphs is that because I decrease the volume, the container is getting smaller. But my amount of stuff is not changing. So initially, all of my chemicals are going to increase. Their concentration is going to go up because they're now in a smaller container. So that's one way to recognize pressure changes. Then I need to think about how will it counteract that stress. So the stress is an increase in pressure. The system wants to decrease the pressure. Now to identify how to do that, I need to look at the moles of gas. On the left-hand side, I have 2 moles of gas. On the right-hand side, I have 1 mole of gas. So the side with a lower pressure is the side with the fewer moles. So the system will shift to the right and make more of my products. So my PCl5 is going to go up and then reach equilibrium. My reactants are going to go down and then reach equilibrium. If I were to decrease the pressure, so now it says I'm increasing the volume, which means I'm decreasing the pressure. Because I'm increasing the volume, I should see that initially all of these concentrations are going to go down because it's the same amount of stuff, but now in a larger container. I have stressed the system by decreasing the pressure. The system wants to increase the pressure. The side with the higher pressure is going to be the side with more moles of gas. So it will shift to the left. It will make more of my reactants and decrease the amount of my products. The last change has to do with temperature changes. Now we do need to remember some things. We need to remember what makes something exo or endothermic. Remember that endothermic reactions have positive delta H's and energy is included as a reactant. In an exothermic reaction, they have negative delta H's and energy is included as a product. So we do need to remember where energy is. If we treat it as a product or a reactant, then we can really treat it as the same as concentration changes. The only thing that we need to keep in mind, though, is that Kc will change for changing temperatures. In our previous examples, the reason why the concentration changes as a result of stressing the system is because Kc is constant. So Kc does not change for those first examples. However, when we change temperature, Kc will either go up or it will go down. To determine that, we need to look at, are we increasing the amount of products or are we increasing the amount of reactants? If I increase the amount of products, that's my number on top, then my Kc is going to increase. I'm going to have a larger Kc. If I increase my amount of reactants, now that number is on the bottom, which means that my Kc will go down. So that number is going to get smaller and Kc will go down. So when we're determining what happens to Kc, for temperature changes only, we need to look at what's changing, whether it's products or reactants. So here we have a system. So here's the Haber process. It says I decrease the temperature. Now we can think of temperature as energy. So if I decrease the temperature, I am decreasing the energy of the system. Now if energy goes down, the system is going to want to counteract that change, so it wants to increase the amount of energy. To determine which way it shifts then, let's look at where the energy is. Here, energy is a product. So in order to increase the amount of energy, the system wants to shift to the right and produce more of it. It wants to shift to the side with the energy. So this system will shift to the right. So my concentration of N2 will go down and then reach equilibrium. My concentration of H2 will also go down. Now it will go down 3 times the amount of N2 because my concentration of my coefficient for H2 is 3. And my concentration of NH3 will go up 2 times the amount of N2 and then reach equilibrium. Now if we think about what happens to Kc, so what has gone up here? My amount of products has gone up. So if we think of Kc as products over reactants, because my products have increased, my Kc will go up in this situation. Now, the next example is what if I increase the temperature? So I increase the energy. The system will want to decrease the energy. Now that means we want to use energy up. Energy is on this side. In order to use up energy, the reaction needs to shift left, because that reverse reaction will be endothermic. It will be using energy. So my amount of N2 will go up and then reach equilibrium. H2 will go up 3 times as much and then reach equilibrium. And then NH3 will go down twice as much and reach equilibrium. If we think about what happens with Kc, now the amount of reactants are going up. So there's a bigger number on the bottom, Kc will go down. And that's how we deal with temperature changes. Temperature changes, again, are the only way that Kc will change as a result of a stress. One other thing worth mentioning is how a catalyst affects equilibrium. Because equilibrium is all about rates, the forward and the reverse reaction, What a catalyst does is it speeds up both those rates equally. So a catalyst will allow us to reach equilibrium sooner, like maybe here, as opposed to here. But it will not actually stress the system and cause equilibrium to shift. So here's an equilibrium mixture that allows us to see some of these changes according to Le Chatelier. I have two different colored ions. I have a pink ion and a blue ion. The forward reaction is endothermic. The reverse reaction is exothermic. Everything's dissolved in alcohol, so changing water will affect the equilibrium. And let's kind of see what happens with some of these different tests. This is the equilibrium mixture originally. It's kind of a pinkish color, but I can do some tests. So for example, if I were to add water, so I'm going to take some water and add it to this mixture, you'll see that it becomes quite pink. So compared to the original mixture, which is more purple, by adding water, the system becomes more pink. Now if we think about Le Chatelier, so the concentration of H2O goes up. The system wants to bring it back down, so it shifts to the left and uses up that excess H2O to make more of this side, where that pink ion is, so it gets more pink. Another test I can do is maybe I can add, so I'll add some silver nitrate. So I put some drops in here. You see that it forms a precipitate, and it also appears more pink. Now this is a case where we need to be careful. I am adding silver ions and nitrate ions. Neither of those are in the system. So we need to be careful and identify what could I be removing. Because we remove ions through precipitation reactions. I can't just reach into this mixture and pluck out a chloride ion. I need to remove it chemically. So what happens is the silver ions react with chloride ions to form insoluble silver chloride. So that's removing chloride ions from the system. Chloride ions, the concentration goes down. The system wants to increase the concentration of chloride ions, so it shifts to the left and produces more of this pink colored ion. The other thing we can change with this equilibrium system is we can change the temperature. I have two beakers here. I have one of cold water, and I also have one with hot water. When I put this test tube in the cold water, it appears more pink. When I put it in the hot water and I give it time, so I'll mix it around, it's slowly becoming more blue. So the temperature actually changes what side the equilibrium lies on as well. If we think about it in the cold water, I've removed energy. In order to produce more energy, the system needs to shift this way. It wants to replace the energy that's been lost, and it appears more pink. In this hot water, I'm increasing the amount of energy in the system. The system wants to decrease the amount of energy, and so it uses it up and shifts to the right to produce more of this blue ion. So it gets more blue when I increase the temperature, and then it gets more pink when I decrease the temperature because it wants to replace the energy by moving that way. You'll see that it appears more pink as it goes in the cold water. This is a quick summary. I'm going to just include this page in your notes along with this instruction. So if you do want to refer back to it, again, remember that the only way to affect Kc is by changing the temperature.